Question 1. Well, given in the tables that the formula book that when theta is small, cos theta is approximately equal to 1 minus theta squared over 2, and sin theta is approximately equal to theta. So we're just going to substitute this into the formula. So 1 minus cos 4 theta is just going to be 1 minus 4 theta all squared over 2, and 2 theta sin 3 theta is obviously just going to be 2 theta 3 theta, just subbing straight in. So next step, just multiply out the bracket. So this is 4 theta times 4 theta, which is 16 theta squared, giving us this here. And obviously 2 theta times 3 theta in the denominator is 6 theta squared. So 16 theta squared over 2 is 8 theta squared. So we're left with 1 minus, and in a bracket, 1 minus 8 theta squared all over 6 theta squared. Well, this is 1 minus 1 add 8 theta squared, so 8 theta squared over 6 theta squared. The theta squareds cancel out, giving us 4 over 3. Question 2. So A, part 1, find dy dx. So if we differentiate each of these terms in turn, so x squared is 2x, minus 2x is minus 2. But bearing in mind this is minus 24x to the half, so multiply by the current power, which is a half, gives us minus 12. Reduce the power by 1, that gives us x to the minus a half. Now part 2, d2y dx squared, we need to differentiate the dy dx. So differentiating the 2x, we get 2. The minus 2 goes, and with this third term, multiplied by the current power, which is minus a half. Minus 12 times minus a half is plus 6, and then reduce the power by 1, giving us minus 3 over 2. Part B, verify that C has a stationary point when x equals 4. So at a stationary point, the dy dx equals 0. So our dy dx from part AI is 2x minus 2 minus 12x to the minus a half. Well, minus 12x to the minus a half is minus 12 over the square root of x. So we need to find when this equals 0. So subbing in their suggestion that we have a stationary point when that x equals 4, let's see if when we substitute in we do indeed get 0. So substituting 4 into this, 2 lots of 4 is 8, minus 2 minus 12 over the square root of 4, which is obviously 12 over 2, which is 6. Now 8 minus 2 minus 6 is indeed 0, so x equals 4 is a stationary point, because when you sub 4 into the differential, you get 0. Part C, well, we can determine whether the nature of the stationary point by working out d2y dx squared when x equals 4. So our d2y dx squared was 2 plus 6x to the minus 3 over 2. So subbing 4 into this, and I'll just pop this straight into my calculator, I've got d2y dx squared being 2 3/4. Now as 2 3/4 is greater than 0, we can conclude that the stationary point is a minimum. Question 3. So we're told that the area of the sector AOB equals 11. Now the area of the sector is half r squared theta. So that equals 11. So that's our first equation that we just park for now and come back to in a minute. Now the perimeter, so the length all the way around the outside, is an r plus the length of the arc AB, which is r theta. So our perimeter in total is 2r plus r theta. Now we're told that the perimeter is 4 times the length of the arc AB, which is r theta. So given it's 4 times as long, then 4 lots of the arc, so 4 lots of r theta must equal the perimeter, the 2r plus r theta. So just going over that again, the perimeter is 4 times the length of the arc. So if we take the length of the arc and times it by 4, so that's 4r theta, we get the length of the perimeter, which is 2r plus r theta. So just divide through by r, we get 4 theta equals 2 plus theta. Take away theta from both sides, divide by 3, we get theta being 2 over 3. So substituting this theta value into our equation number 1, we can see that half r squared multiplied by 2/3 equals 11. So 1/3 of r squared equals 11, multiply both sides by 3, square root, we get r equaling root 33. Question 4, part A. So they meet at this point here, and we're told that x value equals alpha. So where they meet, y equals x equals y equals 2 ln 8 minus x. So these are equal at this point, so x must equal 2 ln 8 minus x. Now if we take away x from both sides, we can say where they meet, 2 ln 8 minus x equals 0. Now if we go and substitute into this function first of all 3 and then 4, if there is a change of sign, then we can say the solution lies between these two values. So let's first of all substitute 3 into this function. So 2 ln 8 minus 3, which is 5, and then take away 3. So 2 ln 5 minus 3 gives us 0.21 ... which is positive. But when we substitute 4 into the function, we get 2 ln 8 minus 4, which is 2 ln 4 minus 4, and that gives us minus 1.22 ... So we can see there's a change of sign between f equaling 3 and f equaling 4. So given there's a change of sign, and given that the function is continuous, these functions are continuous, we can say that alpha must lie between 3 and 4. Part B. Now using the graph and starting with x1 equals 4, determine whether or not this iteration formula can be used to find an approximation for alpha. So using our graph, so we start off at 4 and we go and hit our first curve here, go across to where that reading equals y equals x, then go back across to where that equals y equals 2 ln 8 minus x, back across to the other one, and so on. We can see that it's sort of spiraling inwards in this cobweb diagram. So we can see that we're getting closer and closer and closer to the solution, spiraling inwards here. So for part B, you need to demonstrate this on the diagram and then say that the iteration formula can be used to find an approximation for alpha because the cobweb spirals inwards in the cobweb diagram. Question 5. So we need to differentiate the y function. So our u equals our numerator, which is 3 sin theta, and v equals our denominator, which is 2 sin theta plus 2 cos theta. Now differentiating both of these, so we get du d theta being 3 cos theta, and dv d theta being 2 cos theta minus 2 sin theta. Now the formula for the quotient rule, dy d theta equals v du d theta minus u dv d theta all over v squared. So substituting these four values into this, we get this line here. Now I've then just multiplied out the brackets, so we've done 2 sin theta times 3 cos theta, 2 cos theta times 3 cos theta, and over here 3 sin theta times 2 cos theta, and 3 sin theta times minus 2 sin theta. Bearing in mind we've got the minus, we're taking these away. That gives us this line here, the numerator here. Similarly with the denominator, I've just done 2 sin theta plus 2 cos theta times 2 sin theta plus 2 cos theta, giving me the denominator. Now I can see straight away that on my numerator 6 sin theta cos theta cancels out with minus 6 sin theta cos theta, and so then my numerator can factorize to 6 lots of cos squared theta plus sin squared theta, and in my denominator I can factorize these two together, sin squared theta and the 4 cos squared theta, to get 4 lots of sin squared theta plus cos squared theta plus the 8 lots of sin theta cos theta. Now as we know, cos squared theta plus sin squared theta equals 1, so this bracket becomes 1, this bracket becomes 1, so I'm left with 6 over 4 plus 8 lots of sin theta cos theta. Now, I know that sin 2a equals 2 sin a cos a, and this double angle formula you can just get from the sin a plus b formula that's given in the formula book. So bearing this in mind, multiplying both sides by 4, I can say 8 lots of sin a cos a equals 4 lots of sin 2a. So 8 sin theta cos theta is the same thing as 4 sin 2 theta. Nearly there now. Now go and factorise the denominator, giving me this, and then to really take the 4 upstairs. So the 6 divided by 4 is 3 over 2 as the numerator, leaving the 1 plus sin 2 theta as the denominator. So going back to the what I had to show, I've shown this now. A is a rational constant to be found. Well, my A is 3 over 2. Question 6, part A. So we're told that the gradient of the line L is y equals 2x plus 1. So, the equation of the line L is y equals 2x plus 1. So therefore the gradient of the perpendicular line PA is going to be minus a half. So we've taken the gradient of L being 2, flipped it over, changed the sign, and that gives us minus a half. Now we know that PA goes through the point 7,5 because that's the centre of the circle A, so that's on PA. So given that we know the gradient and we know a point on the line, we can use the equation y minus y1 equals mx minus x1 to work out the equation of the line through PA. So substituting in y1 being 5, x1 being 7, and m being minus a half, we get this. Multiply through by minus 2, rearrange, we get 2y plus x equals 17 as required. Part B, we're being asked to find an equation for C, which is the circle. Now, to work out the equation of a circle, you need to know two things. You need to know the centre. We know that's A, which is 7,5, and then we also need to know the radius of the circle. So we need to work out the length of the radius, for example, the length from P to A. Now, we can only work out P to A once we've worked out what the point P is, and we can work that out because it's where the line y equals 2x plus 1 crosses the line 2y plus x equals 17. So we're going to solve this simultaneous equation. So substituting y equals 2x plus 1 into 2y plus x equals 17, we get this here. Multiplying out the bracket and rearranging, we can work out that x equals 3. And then substituting the 3 back into equation 1, for example, we can see that y equals 5. So the point P has the coordinates 3, 7. So we substituted the 3 back into the y equals 2x plus 1 to work out that y was 7. So P is 3, 7. So let's just do a little sketch to help us gather our thoughts. P is the point 3, 7. A is the point 7, 5. So therefore, if we just create a triangle, the length of the base of the triangle is from 3 to 7, which is a length of 4. The distance between the y coordinates 7 and 5 is 2. So Pythagoras, PA squared equals 2 squared plus 4 squared. So the radius squared equals 20. Now the equation of a circle is x minus the x1 coordinate of the centre of the circle plus y minus the y1 coordinate of the centre of the circle, both of those squared equaling the radius squared. So given that the centre of the circle is 7, 5, we can say that x minus 7 all squared plus y minus 5 all squared equals the radius squared, and the radius squared is 20. Part C. Now we're told the line with equation y equals 2x plus k is also a tangent to C, and we want to work out the value of the constant k. So again, I think a quick sketch to help us gather our thoughts. So we know that P has got coordinate 3, 7, and that's where one of the tangents goes through, y equals 2x plus 1. We've got A in the centre. Now our other tangent's going to be on the other side of the circle. This is a parallel line, believe it or not, going through what I'm going to call point Q. Now to get from P to A, just as this triangle over here that we had, we go down 4 and 2 down, excuse me, go down 2 and then 4 across to get to A. So just by symmetry, to get from A to Q, we're going to have to go another 2 down and another 4 across from 0.75. So 2 down is going to take us, so our x coordinate is going to go from being 7 and then a long 4. So our x coordinate, so that's the bit moving to the right, is going to be 7 add the 4, which is 11. Now our y coordinate at A is 5. It's going to go down a further 2 for Q. 5 take away 2 is 3. So Q has got the coordinate 11, 3. So I've just done that by symmetry. Going from P to A, I've gone down 2 down, 4 to the right, and then to go from A to Q, I've gone down 2 and 4 to the right. So with our second tangent here, we know the gradient is still going to be 2 because it's parallel, and we now know a point on that tangent line. We know the point Q is 11, 3. So again, substituting into y minus y1 equals mx minus x1, we can now work out the equation of this second line, which is also a tangent. So y minus 3 equals 2 x minus 11. So multiplying out the bracket, adding 3 to both sides, we get y equaling 2x minus 19. So the value of the constant k is minus 19. Question 7, part A. So let's just concentrate on integrating 2 over 3x minus k. We'll come back to the definite integral part in a minute. So we want to integrate 2 over 3x minus k. Now I'm going to start off by taking 2 outside the integral, so that's 2 lots of 1 over 3x minus k. Now when I integrate this, I get a third of ln of 3x minus k. And again, just to gather, if you're not able just to do that just on site, I like to think about it the other way around. So if I was differentiating ln of 3x minus k, when I differentiated that, I would get 3 over 3x minus k, being the differential being the numerator and the function itself being the denominator. But I'm not integrating 3 lots of 3x minus k, I'm integrating 1 lot of 3x minus k, so I have to divide through by a third here. So a third of this is what I want, so that gives me, as I integrate and go the other way, that gives me a third of ln 3x minus k. So it's important to be able to go from that step there to it being integrated there. Then obviously just multiplying by 2 I get this. So let's now substitute in the 3k and the k. So substituting in the 3k, I'm going to get 3 lots of 3k, which is 9k minus k. So as I substitute the 3k in, I'm going to get 2/3 ln 9k minus k, and I'm taking away 2/3 ln 3 lots of k minus k. Now obviously 9k minus k is 8k, and 3k minus k is 2k. Now factorising, taking the 2/3 out, and then just the division log rule. So ln 8k minus ln 2k is the same thing as ln 8k over 2k. Now this is key. At this point obviously our k's cancel out, and we've got 8 over 2 being 4, so we've got 2/3 of ln 4 being our final answer for our integral. Now obviously k is now gone, so our answer is just a whole number which is independent of 4. When I say a whole number, I mean a number not dependent on k. So we've just got a number there which is independent of k. So part B, we now need to integrate this here. So again, we'll leave the definite integration bit to last. So let's just concentrate on integrating this. So let's start off by effectively taking the denominator upstairs. So that's going to give us 2 lots of 2x minus k to the power of minus 2 to be integrated. So you may be able to go straight from here to the integrated version. If you can't, let's just sort of think about it the other way around, focusing on the differentiation process. So if we start off with this bracket having added 1 to it, so we've got to the power of minus 1. Let's call y being that, and let's go and differentiate this. So we differentiate, we multiply by the current power, reduce the power by 1, and multiply by the differential of the bracket, giving us this, which simplifies to minus 2 lots of the bracket. Now, this is minus 2 lots of the bracket, but we want 2 lots of the bracket, so we've got to choose to multiply by minus 1, hence why we get this minus in front here. So we've got this as the integral. So this can be written as minus 1 over 2x minus k. I'm just taking this downstairs again. And now for the substituting in. So I start off by substituting in the 2k, and then I'm going to subtract from that when I substitute in the k. So substituting in the 2k, I'm going to get minus 1 over 2 lots of 2k, which is 4k minus k, which is minus 1 over 3k, and I'm going to be adding on to that, then from that I'm subtracting when I substitute k into this, so 2 lots of k minus k is k, so minus 1 over k, so I'm minusing a minus, so I'm adding 1 over k. So I've got minus 1 over 3k plus 1 over k. When we're adding fractions, we need the common denominator, so I've multiplied the second one top and bottom by 3, giving me this. Adding the numerators, I get 2 over 3k, which is 2/3 1 over k. Now, obviously, as we're saying this is 2/3 of 1 over k, this shows that it is inversely proportional to k. So 8 part A. Find the depth of the water in the harbour when the boat enters the harbour. Well, the boat enters the harbour at 6:30, and t is the number of hours after midnight. So 6:30 from midnight is 6.5 hours. So we're going to substitute in when t equals 6.5. So just substituting 6.5 into this, making sure your calculator is in degrees. We get the depth being 4.482 ... so 4.48 meters to 3 sig figs. Part B. So we're being asked to find to the nearest minute the earliest time the boat can leave the harbour. Well, the boat can leave the harbour when the depth is 3.8 meters, d equals 3.8. So solve the equation with this equaling 3.8. So subtract 5 from both sides and divide by 2, we get sin 30t being minus 0.6. So we need to solve this. So let's let capital X equal 30t. So sin capital X equals minus 0.6. So inversing sin both sides, we get minus 36.86. So using our cast diagrams, we can, if we just take a couple of values to start with, because we want to find the earliest time of departure, we can always come back and find more if we need to. So given that, the first values we're going to get is going to be 180 plus 36.8, which is 216.9 degrees. And the second value we're going to get is going to be 360, take away the 36, which is 323. So the first one is all the way around to there, and the second value is all the way around to there. So converting these back until t by dividing by 30, we can say it would be, we could get out of the harbour at 7.23 hours or 10.77 hours, or even later if we want to, but we want to get out as early as we can. Now 7.23 hours is too early, because we're told that the boat enters the harbour at 6:30 and it takes 2 hours to load its cargo. So we can't leave until at least 8:30. So this is going to be too early. So the earliest time we can leave is at 10.77 hours. So converting that into hours and minutes, so it's 10 hours, do 0.77 times 60, gives us 10:46 AM to the nearest minute. So 9 part A. So we're going to start off by differentiating x squared minus 2y plus 3y squared equaling 50. So you work your way along term by term. So the differential of x squared is 2x, and then we're going to take away what you get when you differentiate 2xy. Now when you differentiate 2xy, you get 2x dy dx plus 2y. Now with practice you can do that by sight, but if you can't do that by sight, over here you can see me just working through the product rule, with u being the first term 2x, and v being the y. Differentiate, dy dx being u dv dx plus v du dx. You will see how we get the 2x dy dx plus 2y. So moving on to the third term, when we differentiate 3y squared, we get 6y dy dx, and when we differentiate the 50, we get 0. So that gives us that line here. And then I've just really done the claw here. I've just multiplied out the bracket, so that's how we get the minus 2x dy dx and the minus 2y, taking us to this line here. And then I've just kept all the terms involving dy dx on the left and moved to the right hand side the terms that don't include dy dx. So that takes us to here. Then I've factorised, so we've got 6y minus 2x dy dx equaling this. Divide through by the 6y minus 2x, we get this. Then dividing through by 2, each of the four terms by 2, we get y minus x over 3y minus x as required. Part B, so using part A, so using this up here, find the exact coordinates of the point P. And we're told that P and Q represent the points that are furthest west and the furthest east. So what we can see at P and Q, they're not maximum and minimum. It's not when you differentiate you get 0. Quite the opposite. If you differentiate at P and Q, the differential is going to be approaching infinity. So for that to be the case, you're going to need the denominator of the differential to be equaling 0. So we can just solve 3y minus x equaling 0, giving us y equaling a third of x. So we take this and we substitute this back into the curve that we're given right at the beginning. So substituting y equals a third x into the curve, working through the algebra, we get x being equal to either plus or minus root 75. Now p is obviously to the left, so p is going to be when x is minus 75, q would have been when x was plus 75. So at p we know that x equals minus root 75, which simplified is minus 5 root 3. So that's the x coordinates. Now for the y coordinate, we just substitute that x value into y equaling a third x, giving us y equaling minus 5 over 3 root 3. So the exact coordinates of the point P are minus 5 root 3 minus 5 over 3 root 3. Now part C, explain briefly how to find the coordinates of the point that is furthest north of the origin. Furthest north of the origin, well that's going to be the maximum at the top where the differential is 0. It's where this curve is going to be the horizontal line. So we're going to solve where dy dx equals 0. So going back to our differential, if dy dx is going to be 0, then y minus x, the numerator, is going to have to equal 0. So x is going to equal y. So how would we do this? We just substitute this back into the curve. And then once we get the two possible solutions, we would choose the positive solution, because the negative solution will be giving us the point over here, which is further south of the origin. Question 10, part A. So we can rewrite this as the integral of 40 over h dh equaling the integral of cos 0.25t dt. So this is the key opening line. So how have we accomplished that? We've really rearranged this. So think of it as multiplying through by 40, dividing by h, and multiplying by dt. So we've got all the h's on one side and all of the t's on the other. So we've got the h and the dh and the t and the dt. So let's just do those two integrals. So the integral of 40 over h is effectively the integral of 40 lots of 1 over h, which is 40 ln h. And integrating cos 0.25t, we get 4 lots of sin 0.25t plus c. So dividing both sides, dividing through by 40, we're going to get ln h equaling 0.1 sin 0.25t plus c. Now to work out the constant, we're given a fact. We're given that at time naught, the passenger is 5 meters above the ground. So when t is naught, h is 5. So substituting that into the equation, the sin of naught is naught, so we basically got ln h equaling c. So our revised equation including c is this here. Now to rearrange this, let's start off by minusing ln h from both sides, and then using the division log rule, we can say that this is ln h over 5 equaling this. So really undoing the ln, we can say h over 5 equals e to the power of 0.1 sin 0.25t. Multiplying both sides by 5, we get what we had to show. Part B, state the maximum height of the passenger above the ground. So let's think about the formula. Now to maximize this, we are going to want the sin 0.25t to equal 1. That's the maximum value we can get from the sin curve. So we get h is going to be 5 lots of e to the power of 0.1, which is 5.53 meters to 2 significant figures. Now, part C follows on from part B. In part B we established that we needed sin 0.25t to equal 1. So think about our sine curve. Where does the sin curve equal 1? Well, that's at pi over 2 and 5 pi over 2 to start with. Now we're interested in when the passenger reaches the maximum height for the second time, so that's at 5 pi over 2. So our 0.25t has got to equal 5 pi over 2, so t equals 10 pi, which is 31.4 seconds. So 11 part A. So let's start off by rewriting this as being the square root of the numerator divided by the square root of the denominator. So that is 1 plus 4x to the half, and then taking the square root of the denominator upstairs, that's going to be 1 minus x to the minus a half. So big opening step. Make sure you can go from the left hand side to that opening step, which obviously then allows us to use the binomial expansion. So using the binomial expansion on 1 plus 4x to the half, we get this, just substituting straight into the formula, which simplifies to 1 plus 2x minus 2x squared. And then the 1 minus x to the minus a half, again just substituting straight into the formula, we get this, which simplifies to this equation here, which I've called equation number 2. So multiplying the two together, we obviously get this times this, being this times this, and then really just looking at where we're picking up our normal numbers, our x's and our x squareds. The only normal number we're going to get is the 1 times the 1. How are we going to get x's? Well, we're going to get x's when we do the 1 times the half x and the 2x times the 1. And then how are we going to get x squared? Well, that's going to be when we do 1 times the 3x squared. Our 2x times a half an x gives us the x squared, and our minus 2x squared times the 1. So those are all our normal numbers, our x's and our x squareds. Gathering up like terms, we get what we indeed had to show. Part B. Now for the expansion to converge, so sort of to get smaller and smaller and smaller, each term getting smaller as you add them, rather than sort of exploding outwards, you do need this term here, the modulus of the 4x, to be less than 1. Otherwise, when you do it, the expansion, the terms keep on getting bigger and bigger and bigger, rather than smaller and smaller and smaller. So, so the modulus of 4x has got to be less than 1. So dividing through by 4, then obviously the modulus of x has to be less than a quarter. So we shouldn't use a half, because obviously a half is greater than a quarter. Part C. So we're instructed to substitute an 11th into this. So let's start off doing so on the left hand side. So substituting 11th in, just sort of follow this through, you see I end up with root 3 over root 2. Now I've then factorised that by multiplying top and bottom by, not factorised it, sorry, I've rationalised that, excuse me, by multiplying top and bottom by root 2, giving me root 6 over 2. So what we can see is that substituting an 11th into this gives me root 6 over 2. So if I want to find an approximation for root 6, if I substitute an 11th into the right hand side, that will give me what root 6 over 2 is, so I then just simply double it to get back to my root 6. So substituting an 11th into the expansion, I get this here, which simplifies to 1183 over 968. Now that, as I said, is root 6 over 2. So for an approximation for root 6, I'm going to double this, giving me 1183 over 484. Question 12, part A. So I'm given two facts. I'm told that the car was worth 32,000 on the 1st of January 2005, and that was 4 years after it was first valued. So we can say when t is 4, the v equals 32,000. And the second fact we're given is that it was worth £50,000 on the 1st of January 2012. Well, that's 11 years later. So when t is 11, v equals 50,000. So if we substitute both of these in, we get two equations, so we can solve this simultaneous equation. So if I take this second one, call it equation 2, the first one being equation 1, if I do 2 divided by 1, because I've got a divided by a, they cancel out. P to the 11 divided by p to the 4 is p to the 7. So p to the power of 7 equals 50,000 over 32,000, which is this, which rounds to 1.0658 to 4 decimal places. Now for part 2, I've been asked to show that A is approximately 24,800, so I obviously just substitute that back into one of the equations. So I'm going to substitute it back into equation 1. So 32,000 equals A p to the power of 4, so that's going to be A times 1.0658 to the power of 4, giving me 8 being 24,796, which is approximately 24,800 as required. Part B. So with reference to the model, interpret the value of the constant A and the value of the constant P. Well, A is going to be the value that the car was worth right at the beginning. So the 24,800 represents the value on the 1st of January 2001 when t was 0. And P, it was 1.0658. Well, that's the factor by which the value of the vintage car rises each year. Part C. So using the model, find the year during which the value of the car first exceeded £100,000. So let's go and set up our equation, and we're looking for it when it first is greater than £100,000. So we now know what A is, 24,800, roughly 24,796 to be more precise. We know that P is 1.06583 ... So we're setting this up to be greater than 100,000, and we're just solving for t. So I've divided through by the 24,796.80, and at that point I've taken log. So I've logged both sides, and then using the power rule I can say t log 1.0658 is greater than log 4.0327. So then dividing through by log 1.0658, I get t being greater than this. Popping that into your calculator, I get t being greater than 21.87. So it's going to first exceed £100,000 during the 22nd year. So in what year does it first exceed it? So it's after 21 years, but it's before 22 years are up. So it's in the 22nd year. So therefore, working forward from when it was first valued, 1st of January 2001, that means during 2022. Question 13. Now, this question could be answered by substitution. It was perfectly possible to use a couple of substitutions to answer this question, but I've chose to do it by integration by parts. So I'm using this formula up here, which is given in the formula booklet. So I've let u equal 2x, and I've let dv dx equal my square root of x plus 2, which is x plus 2 to the half. So differentiating 2x, I get 2, and integrating x plus 2 to the half, I get 2/3 x plus 2 to the power of 3 over 2, which I've just explained the working over here if you can't just do it by sight. So just plugging that into the formula, so I've got u times v, so the 2x times the 2/3 x plus 2 to the power of 3 over 2, and then I'm taking away the integral of v, which is 2/3 x plus 2 to the 3 over 2, times du dx, which is the 2. So just multiplying the 2/3 by the 2, that gives me 4/3 x plus 2 to the power of 3 over 2 to be integrated. Now, I think the secret here, what makes this to sort of much easier, this second integration, is to choose to let u equal the 4/3. So choose to let u be the 4/3, your dv dx being the x plus 2 to the 3 over 2. It's because once you then differentiate the u, du dx equals 0, so that's going to make a lot fall away in a minute. So we've made the x plus 2 to the power of 3 over 2 the dv dx, so integrating that we get this, and I've just shown the workings for that down there. So back to then this sort of second integration. So again, by parts, we're saying it's u times v, so 4/3 times the 2/5 x plus 2 to the 5 over 2. But when you're taking away the integral of v du dx, because du dx equals 0, that just becomes 0. So we sort of get to the end of having to integrate. So just tidying up this second part here, 4/3 times 2/5, I get 8 over 15. And then I can, so that's basically my integration done. So I'm then going to start off by substituting 2 into this, and then secondly substituting 0 into this. So substituting 2 into it, I get these two terms, and then take away what I get when I substitute 0 in, I get this, which simplifies to this. And then just following through the algebra, I can end up with my 32 over 15 multiplied by 2 plus root 2 as required. Part A. Now I thought this was an awful lot of work for 2 marks, but then I guess it is the last question on the paper. So your thought process is we need some way of linking cos 2t to sin t, something that's an equation that has this on one side and really allows us to get sin 2 on the other side. So my focus has been to kick off with the cos 2t. So I'm really starting off using the cos a plus b formula, which is given in the formula booklet. So just letting a equal b, a and b both equal t, we can see we get cos 2t equals cos squared t minus sin squared t. Now we also know that sin squared t plus cos squared t equals 1. So rearranging that, I can make cos squared t equal 1 minus sin squared t. And then if I substitute this second equation into the first equation, I end up with this formula here, which is really what I wanted. I've got cos 2t on the one side, and then I've got sin t on the other. Oh, yeah, albeit it's sin squared t, but obviously that's just sin t all squared. So really this is the bit that allows me to get y equaling x, because I can manipulate this to equal y, manipulate this to equal x, and then I've got formulae involving y equaling x. So let's start off with y equaling 4 plus 2 cos 2t, and then I'm just going to rearrange this so I have cos 2t being the subject. So I've taken away 4 from both sides, divided by 2, and that gives me y minus 4 over 2 equaling cos 2t. And then I've just parked that for now. Now then, going back to my x equals 3 plus 2 sin t, and I'm now going to manipulate this as well to equal cos 2t. So I've taken away 3 and divided by 2. I've then squared both sides, and then because I want it to equal this, I'm then saying 1 take away 2 lots of that. So that gives me 1 minus 2 sin squared t, which equals cos 2t. So I've now got 2 equations which both equal cos 2t. This first equation here is y minus 4 over 2 equaling cos 2t, and this one over here also equals cos 2t. So these two bubbles in light blue I can make equal to each other because they both equal cos 2t. So I've then just applied the algebra to make y the subject. So I've multiplied by 2, I've added 4, tidied it up a bit, and that allows me to show what I had to show, the y equals 6 minus x minus 3 all squared. Part B, so we've got to draw the graph, the curve C. So it's a minus x squared graph, so we know it's going to be a negative parabola shape, sort of a sad face shape. Now, from completing the square, we can see here, given this isn't rather in completing the square format, we can just see that the maximum point is going to be at 3, 6. So we want to maximize the y value. To do so, we've got to make the bracket equal to 0, because anything squared, the biggest it can be is 0. So what makes this bracket 0? That's when x is 3. And then when x is 3, what y value do we get? We get y being 6. So we know the maximum point is at 3, 6. Now let's think about x equaling 3 plus 2 sin t, and t's going from 0 to 2 pi, so from 0 to 360 degrees. Now over that t range, our sin values are going to fluctuate between -1 and +1. So our x is going to fluctuate between 3 plus 2 lots of -1 and 3 plus 2 lots of +1. So that gives us a range of x values from 1 to 5. So from 1 to 5. Now what y values do we get for each of these x values? Well, I've just substituted these x values into the part A equation, which involves y and x, giving me y values of 2 and 2. I've forgotten to put the 2 in there, but that should say y equals 2. So we've got 1, 2 and 5, 2. So that is the shape of our graph. Now for B part 2, explain briefly why C does not include all the points on this curve. Well, we've just seen that our x values are restricted to between 1 and 5. So we don't have any values for x below 1 or above 5. So x is less than or equal to 5 and greater than or equal to 1. Now, part C. So we're told the line with the equation x plus y equals k, where k is a constant, intersects the curve at 2 distinct points. I'll do a sort of little sketch over here to help with my explanation throughout this part. So we've got a line x plus y equals 7, which is something like that, and it's intersecting the curve twice. So where does it intersect? It intersects where the curve equals the line, so we can solve the simultaneous equation with y equaling k minus x, the line, and y equals 6 minus x minus 3 all squared, the curve. So set them equal to each other, rearrange to get a quadratic equaling 0, and we get this. Now we've got two intersections, we've got 2 distinct points, so we've got to have 2 real roots, so we know the discriminant b squared minus 4ac has got to be greater than 0. So a is 1, b is minus 7, c is 3 plus k. Substitute that into the discriminant formula, and we can see that k has got to be less than 37 over 4. So k has got to be less than 9 1/4. So that really represents this tangent at the top. So x plus y equals 9.2. That is a tangent. You would only get one solution there. So we're looking where x plus y is less than 9.25. So our biggest value of k is we're going to be saying in our in the inequality is that k has got to be less than 9 1/4. Now, what about the minimum value for k? So think about a parallel line to this x plus y equals 9.25 coming downwards. So the parallel line, so x plus y is just getting a bit smaller, a bit smaller, a bit smaller. Well, eventually we're going to get to the point where x plus y equals 7. That would be the very last time we have our second distinct solution. Anything less than x plus y equals 7, this line will still cut the curve over here, but it will miss this curve at this end. So our x plus y equals 7 is the very last time that k will give us two distinct roots. So therefore we can say that k is greater than or equal to 7, and at the same time has got to be less than 9.25. And then remember to give your answer in set notation as required.